All right, ladies and gentlemen, so today we are going to talk about winds. Okay, so for those of you who are following along in your review book, we're on pages 131 to 132. All right, so things that cause the wind to blow, that's basically what you want to figure out. It's going to be pressure. It's all about pressure. Depending on if it's high pressure or low pressure, that's how you're going to figure out which way the winds are going. This is how those weather people are able to guess, because you can't really predict the weather. You kind of go with the flow. You're like, it could go here or it could go here, depending on how the storm runs, which is why the snowstorm that we had in my neighborhood had almost 18 inches of snow, but in some neighborhoods they just got rain. Okay, when we were supposed to get, like, I think 6 to 12 was originally what they had said. All right, so here we have the pressure. So why does the pressure mean anything? Well, if it's high pressure, right, it means that you're squeezing the molecules together. When you squeeze the molecules together, it means they become more dense. It all comes back to density, right? Versus in low pressure, right, they are going to be able to separate apart, which makes them move more, which means they have more average kinetic energy, which makes their temperature increase, and then they rise up. All about convection currents, okay? So let's talk about actual pressure and how it relates to wind, right? So we have wind in general, all right? It's always going to move from high pressure systems to low pressure systems. Now, if that H was not there, how do we know that it's a high pressure system? Well, let's look at the values. Remember, these are isobars. Right, let's look at these isobar values. As you go into the center of the whole system, the numbers are increasing. That's how you tell if it is a high pressure system or a low pressure system. Okay, now it's always going to move from high to low. It kind of looks like the infinity symbol, right? Except it just doesn't come back. All right, in low pressure, again, you're going to look at the millibar values, and they decrease as they go in. So if there's not a big H there or a big L there, that's one way that you can determine what type of a system we have. So we're going to watch a little video or commercial first.
Try Febreze Small Spaces. Just press burn, and it continuously eliminates odors in the air and on soft surfaces for 45 days.
All right, so nobody said that scientists weren't corny as hell. It's okay. All right, so like he said, it has all to do with the fact that we rotate. If we didn't rotate, we wouldn't have these jet streams or pressure variances or changes in climate. There's so many things that, because we rotate, and we prove that we rotate, happen. Okay, so let's look. A little bit of things work. All right, first of all, we need to know how is pressure actually figured out, right? Right, there's an anemometer, right? So when you're looking at pressure, right, we talked about pressure and how it was measured through a barometer or the other one, right? But this is part of wind. You see these little cups here, right? They catch the wind, and you can figure out how fast or slow they are moving. Okay, this is one of the original ones. Pretty cool. All right, so let's talk about high pressure. All right, now this is just a typical weather map. You guys have been watching the weather over the last couple of days, especially because of the snowstorms, hopefully. And there's a lot of stuff on here, including these symbols. All of these symbols and everything that you're going to need to know about weather and weather stations are on page, let's find it, in your reference table. It is page 13, down at the bottom here. Okay, so we have our pressure changes from millibars to inches at the top, right? And then down here at the bottom, we have what's known as weather stations. This weather station map down here has we're going to be looking at fronts specifically in a few. All right, we've talked about different weather topics here a little bit. We'll get more into this. It's kind of like the culmination of all of weather when you're looking at it, because it gives a little bit of everything. But I want you to keep that page specifically in mind. okay, because it does have some symbols on there that will help you later. All right, so just by looking at this map, I can see that I have some high pressure systems on the left over here. I have a low pressure system here, right? I have a cold front and a warm front coming through. Okay, well, how do I know these things? Well, first of all, capital H stands for high pressure. Very simple, very easy. Capital L stands for low pressure, but there are other indicators on here that are telling me this. So let's look. When you have high pressure, what actually is happening? Well, the winds at the center are moving out. They're going to move out from the center, okay? They're going to move out and clockwise, all right? They're not only going to move out and clockwise, but they're also going to move down. So it's down, out, and clockwise. I want you to think of a ball gown, guys, all right? When you think of a ball gown, it's small on top, and then it flares out at the bottom, okay? That's what a high pressure system from the inside looks like, okay? And all of the wind around it is going to go down and around in a clockwise fashion, all right? In those high pressure systems, you're going to have dry weather. Notice how in this picture, there's no green or white or pink around them. Why? Because those indicate storms or precipitation, right? Anytime you have a color around it, it really does look like precipitation. So it's going to be very dry. So if you have a high pressure system, it's dry. So we say high and dry. So when you have the winds, they go down, out in a clockwise fashion, okay? And the weather around them is dry. Now, there is no place on the reference table that gives you this information. Instead of memorizing both high pressure and low pressure systems, what you should do is memorize one of them because it's the opposite that's happening in a low pressure system, okay? Which brings me to low pressure. Oh, sorry. The high pressure is also known as an anti-cyclone. I would definitely highlight that, okay? Because it's the opposite of a cyclone. When you think of a cyclone, you think of a hurricane or a tornado. When you think of a hurricane or tornado, you think of that small little piece that comes down and it's circling, right? But at the very top, it's almost like a ta-da, it's like a mushroom. Hey, I'm here, okay? High pressure systems are just the opposite. They are the upside down mushroom or an upside down Y, okay? So low pressure systems are the complete opposite, which means that the winds are going to be moving in to the center, okay, in a counterclockwise fashion. So when they come in and counterclockwise and up, okay, remember converges means comes together and then rises up, okay. Now just by looking at the map, we can tell that if you have a low pressure system, that's where the precipitation is going to come in. So it's not only that you're going to have L for low pressure, but you're going to have L for lousy weather, like stormy weather. Okay? And remember, just like in temperature, it goes from high to low. So winds are going to move from high pressure systems to low pressure systems. And if you think about it, it makes sense, right? Because if the wind in a high pressure system is moving down and out, right? In a low pressure system, they're going to move in and up. Okay, so one feeds into the other. So it's literally like down over here, up. Okay, so that's exactly what happens. And a low pressure system is known as a cyclone, right? Because it has those converging winds that can make them go up, all right? And here's both of them at the same time. So in a high pressure system, at the top it converges, goes down and diverges out, moving towards the low pressure system, which then converges down at the bottom, goes up, and then diverges, all right? So in other words, it goes down and out in the high pressure system, and in a low pressure, it goes in and up and out. Okay, and I hope you guys all think of this when I talk about a low pressure system. Okay, this map here, I was just talking about weather stations a minute ago, right? This is a black and white map of a specific area. These little dots and squares and little leaves that you see here, okay, these little feather things, those are all part of a weather station. There are certain parts that we have weather stations set up so that you can take individual readings. Who knows what this symbol is right here, down here? This thing here. What is this?
Isn't it a hurricane?
It's the eye of the storm, and it represents a hurricane. And if you didn't know, look, our handy dandy reference table down here at the bottom. Okay, kind of looks like that hurricane, right? So what is that going to tell me? Yes, it's the eye of the storm because it's in the middle. But what is it going to tell me about the winds here? Look at the map. What is it going to tell me about the winds that are here?
They're going to be wind.
They're going to be one at a time. Which one do you guys want to go first?
You go ahead, buddy.
Wait. What was the question?
So right here, where the hurricane or the eye of the storm is, what is that going to tell me about the winds?
They're going to be way higher or way more intense.
Why?
How
do I know?
Closer together, just like a topographic map.
What's closer together? Help me out here. I know nothing.
Wind or...
But how do I know that that's going to be where the strongest wind is? Because you're right. But how am I going to know?
It's closest to the center?
It's closest to the center, yes. But you started saying it like a topographic map. Why were you saying like a topographic map?
Because the closer the lines are together, the steeper the gradient is.
Yes! Victory! Right? So the closer the lines on a topographic map together they are, the steeper the gradient is going to be. But we're not looking at a topographic map. We're looking at an isobar map or a pressure map, right? Which is going to tell me the same rules apply. The closer the lines that are together, the higher the pressure, the heavier the winds. So where am I going to look? So, Owen, I want you to back off this one question, okay? I want to see if somebody else can get this. Where on this map will be the lowest winds?
To the top left.
To the top left, exactly. Who is that?
Brandon.
Good job. Okay, so you're correct in the top left. Now, Brandon, tell me, why would the top left be the lightest winds?
Because the lines are farther apart, so like I guess building off from what Owen said, the winds wouldn't be as intense.
Good job. All right, so when you were looking at this, it doesn't matter if it's a topographic map, if we're looking at a temperature map, if we're looking at a pressure map. Whenever the lines are closest together, you're going to have the steepest or heaviest or strongest, okay? Anytime that the lines are furthest apart, it's going to be the weakest. It's going to be the lightest, any of those versions, okay? So it doesn't matter what type of map we are looking at. If we're looking at contour map, if we're looking at a temperature map, if we're looking at a pressure map, whatever it is, the same rules apply. Good job, guys. All right, so how do we draw winds around high and low pressure systems? Well, just like this, right? You're going to show that the high pressure systems are going in a clockwise fashion, okay? And that in a low pressure system, they're going in a counterclockwise fashion. All right, simple and easy. So let's look at some practice questions. Now, remember I said, you're not always going to have that capital H or capital L inside of the system, and you're going to have to figure it out. But there's no numbers on here. So how am I going to figure out if this is a high or a low pressure system?
It's a low pressure because the arrows are going inward, meaning the wind is going inward.
Okay, does anybody agree or disagree?
I agree.
Agree?
I agree.
I was going to say, there's like 30 of you guys in here, and I've only heard from 4 of you.
I agree.
Good. It is a low pressure system. So if it's a low pressure system, are we talking about dry or are we talking about moist? Are we going to have dry or are we going to have lots of precipitation?
Moist.
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 Very good. Good job. All right. So here's a throwback question. Which direction do winds curve in the northern hemisphere?
Can I go?
Go ahead.
I believe it's to the right.
Agree or disagree?
Agree.
He's right. It could go. It's
Agree.
one of, and I think it's to the right.
I agree.
You're all correct. Very good. Okay, now why is it to the right?
Coriolis effect.
And what does the Coriolis effect tell us?
I always was
That the
stuck.
Earth is rotating.
Exactly, guys. See, I told you guys from the beginning of the year, this stuff doesn't go away in earth science. It builds on each other, which is why I've been pushing you. If you're not doing well on the midterm, or if you don't remember things from the first quarter, come to extra help because it's all coming back. The Earth's rotation stuff we did in first quarter. Coriolis effect we did in first quarter. Well, that's going to help us with everybody's most hated reference table, as you guys remember, is coming back. That one, right? The one with all of the winds and the convection currents and the wet or the dry parts. Now, speaking of that, I want you guys to all, actually, I'm going to skip this for 1 second, okay? I want you guys to all look at your reference table, at everybody's most hated reference table. So it's page 14. Right here. Okay? Is everybody on it?
Yeah.
Getting there.
Okay, so we were just talking about how winds move from what system to what system?
High to low.
High to low, right? Now, in a high pressure system, what kind of weather do you have?
I think it was
Dry.
Bad weather.
It's dry, right? In a low pressure system, we have
Moist.
moist or wet or a lot of precipitation, right? Now look here. Remember how I said they crammed a whole ton of information on this one reference table? Well, let me refer to you again to it, right? Well, we said it moves from high to low or dry to wet. Look at the winds. Dry is at 30 degrees south, and it's moving towards the wet weather, right? Dry is at 30 degrees north, and it's moving towards the wet weather. Ooh, the answer is here for you. Right? So when you are thinking about these things, this actually gives it away for you. Okay? It also shows you that as you are in the northern hemisphere, the winds are going to move towards the right. Right? And if you're in the southern hemisphere, it's going to move towards the left. So if you're standing here and you're moving south in the southern hemisphere, it's still your left. Okay? So just remember that, right? And it also always moves from dry to wet, right? Just wanted to kind of give you the heads up as to where we're going. All right. So is this clockwise or counterclockwise? Are we going clockwise or counterclockwise?
Clockwise.
clockwise.
Very good.
Clockwise.
So if it's clockwise, is this a high pressure or a low pressure system?
Hi.
Agree or disagree?
Agree.
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 Good. Okay. So if it's a high pressure system, are we talking about moist or dry?
Dry.
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 Good. So it sounds silly, but that was kind of like a mini quiz for you. Okay. So now we're going to talk about a sea breeze versus a land breeze. Okay. So remember when we did a solar eclipse versus a lunar eclipse, and that first word gave it away, right? The fact that it says a sea breeze or an ocean breeze is telling me that the breeze is coming off of the water. Okay. Now this is only going to occur during the day. And the reason it's only going to occur during the day is because you have more insolation, right? When you have more insolation, you know from our lab, that lab is going to come back. So if you don't understand it, you got to tell me. All right, the land heats up faster. Why does the land heat up faster?
It has a lower specific heat.
Exactly, right? What does that tell me if it has a lower specific heat?
It heats and cools faster than water.
Takes less
But why? Why does it heat up and cool down
because it
faster?
takes less energy too.
Due to its material, it raises by a degree quicker.
Hold on. Owen, who was just talking? Was that Brandon or Sosa?
Yeah, that was Brandon.
Brandon, tell me.
Yeah, Brandon.
Brandon, what were you just saying?
Because it takes less energy too.
To do what?
To heat up.
Exactly. So the fact that it has a lower specific heat capacity tells me that it's going to need less energy to increase the land by 1 degree, right? Remember in the lab, when we did this, right, the temperature, we had both beakers here, but the temperature of the water stayed where the temperature of the land was like boop, 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 and then eventually the land was like, oh, we're going to move now? Boop, 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 boop. And the land kept heating up where the water did not. Okay, so what happens is that as long as you have that sunlight, that land is going to continuously heat up, which is why when you're over here, you run to as close to the water as you can because your feet are burning, feet are burning, feet are burning, feet are burning, and then when you get closer to the water, they're not burning as much anymore. Okay, so the land is heating up, and it's heating up, and it's heating up. So that means the molecules are moving faster, right? And they're moving further apart, making them less dense. Well, then that happens, they rise up. When they rise up, they move away from the heat source. And when they move away from the heat source, they cool down and they come closer together. When they come closer together, they become more dense and they fall down to the ground. And then they breeze on over to the low pressure system. Okay? Now, I want you to pay attention really quickly. Notice how because it's an ocean breeze, the breeze is coming off the ocean. Makes sense, right? Well, watch the picture. Wait a second. What just happened here? Oh, wait. Miss G, you said that it has come off the ocean, but the ocean's on the left in this picture, and the ocean is on the right on this picture. Exactly. You have to be careful, okay? You have to be careful and make sure that you know where the water is. Do not assume that it's always going to be on the left because within 2 seconds, the water was now on the right, okay? So wherever the air is falling and cooler, that's where you're going to get your high pressure system, okay? Wherever it's warmer and because they move further apart, that's where your low pressure system is, okay? So for a sea breeze, the cool air is coming off of the sea. For a land breeze, okay, is where the land is going to have the cool breeze coming off of it. And it only occurs at night. And the reason for that is because of the fact that water has that higher specific heat capacity, which means that it's going to take longer to cool down. So here we have our warm air, right? This is just a convection current. Wherever the heat source is or that warm air is, it's going to heat up, bring the air up away from the heat source, having a high pressure system down here, which cools it off, and then it brings it back over the water. So remember, if it's a sea breeze, the cool breeze is coming off of the sea. And if it's a land breeze, the cool air is coming off of the land. Okay? And again, right? All I did was switch where the water was.
Miss Gonzalez.
That better?
Miss Gonzalez.
What's up?
No. I just have a question. Like, when you said it hits the sea, right? You said it gets colder and the molecules get denser and they start to fall, right? So how does it kind of rise when it hits?
For a land breeze, it's the opposite because now your cooler surface is on the land because there's no more insulation coming in to warm it up. And since it has a lower specific heat capacity, it releases that heat really quickly. So the sand itself will feel cooler than the water at night.
Okay. Oh, I didn't see that part about night. Yeah,
So
thank you.
land breeze only happens at night, where a sea breeze only happens during the day because you need that insulation. Okay? Now, we're going to move on a little bit. So the isotherms we've already talked about, right? Isotherms are just temperature lines. It's just like a contour map. Instead of we're talking about just iso lines, these are specifically for temperature values, right? So how do things vary in temperature? Well, if a variation is to change from the average value, the first factor is going to be latitude. Okay, so how things change in temperature, right? Well, the higher the latitude, right, the further away you get from the equator, the cooler the temperatures will be. That's not anything new. We know this. If you could go away during February break, I doubt you're going to go to the North Pole, right? It's been snowing here. It's been cold here. Most people during February break, if they can, will go towards the equator, the Caribbean, Mexico, Florida, right? Somewhere down south. And right now, guys, Florida's only like in the 60s, so it's not super warm, believe it or not. But it's still warmer than here. So the closer you get to the equator, the lower your latitude is, the higher the temperatures. The higher your latitude, the lower the temperatures. That should not be a shock to the system, seeing as if we've been talking about this all year long, right? So if we are in the United States, the things that are closer to Canada, the states that are up here closer to Canada, are going to be colder than the states that are closer down here to the, to the equator. Okay, in comparison to this. Now, there are other factors as well, which we already started learning about, like inland versus coastal cities. This is all coming back, right? So cities by the water are going to experience cooler summers and warmer winters because we're surrounded by that water, which during the winter keeps us a little bit warmer compared to inside where they're not. If you looked, did you guys all watch the weather while you were waiting to find out if we had a snow day? Yes, no, maybe?
I was just looking at
No, I don't.
Okay, so what you guys need to do is, if there is a chance of snow, just take 5 minutes out of your day, 5 minutes, and watch the weather. I don't care if it's the Weather Channel. I don't care if it's News 4, News 12, News 47, whatever, Telemundo. I don't care, okay? 5 minutes. And I want you to notice that whenever there's a chance of snow, they always say north and west of the city is going to get higher snow totals than where we are on Long Island. Okay, I just want you to notice it because they're more inland, which means they are not surrounded by the water, which would keep them warmer, right? So since they're not surrounded by water, they're much colder in there, which means they usually get slammed with snow. Okay? Now, the last factor that you need to know on how it varies in temperature, and I believe that's the end of the period after this, okay, is elevation. So as the elevation or the altitude increases, we know that the temperature decreases. So if you were to compare from the bottom of a mountain in the same location as on the top of the mountain, the temperature at the top of the mountain is going to be colder, right? Because there's more air molecules in between each of them. There's more space in between each of them. And if you don't remember, you could always look on your reference table page 14, right? That's 14. Yes, page 14, right? The temperature versus altitude, right? And there we have our snowy mountain. Snow is at the top is much colder than down at the bottom. All right, guys. So that's where we are going to end today. You do not have any homework. I'm going to be posting the quest for you. Okay. But that's about it.